And that's it. That's it. So what we want to do is find the rectangle areas, sign included. All right, so there can be positive area, there can be negative area. Find those areas, add them all up, find the net area, and then divide by n minus 1 to get a sort of a bias adjusted average area. Just think of it as average area, right? So we want to have an average area. Is it net positive or negative or zero? That is what we want. And then because of the way the definition is designed, that it sort of subtracts off the average, x bar and y bar. When the covariance is positive, all right, so when covariance sample is positive, we will get a sort of a positive gradient line with positive gradient. All right. And if it is negative, then we get a line with negative gradient. And if we have 0 exactly, then it implies that there is no line being perceived. Of course, it is mathematics, but it's kind of cute, and rather if you look at it as being run by a robot, then it is quite meaningful to say no line perceivable by the robot. The robot cannot see a line. Okay, so that will be also very important, valuable information to deduce from. Remember, a cloud of points that can be 1,000, 1,000,000 points spread all over on this graph, and we want a single number summary of the strength of being a line. How linear is the linearity of the data points? Yeah. So this is the power of it, and therefore, even though the formula looks a little bit complicated, you find that it's a must, right? It's so natural that we insist that it has to be the case. And so you don't have to memorize it. In fact, it pops out right away if you can appreciate the need for a single number summary of these two-dimensional data points. And that is fantastic, because when it's two-dimensional, it also invokes very strong visual aspects of it, right? As we plot on the XY axis. Yeah. Another way to think about it is that if most of the data points are clouding around quadrants 1 and 3, then we do have some sort of a linear indicator, right? So if the points are clouding around quadrants 1 and 3 with occasional outliers, stray data here and there, that the net negative areas will not be sufficient to minus off so many and so large positive areas induced by the data points in quadrants 1 and 3. So then, isn't it fair to say that it is actually a line, because it's 2 pixel LED, right? So it's like a 2x2 camera, so low in resolution that if you light up most of the pixel 1 and 3, that is a line. Yeah, something like that. So it's although it's kind of like super low resolution camera, it nicely summarizes, right? It nicely and objectively throws out information that confuses us, yeah, and distracts us from concluding that it is being linear. And likewise, if most of the points are in quadrants 2 and 4, with occasional outliers in quadrants 1 and 3, and doesn't matter how outlying they are, you can now imagine, right? The net negative areas induced by these outliers will not be sufficiently strong to change the net positive areas induced by these outliers will not be sufficiently strong to cancel off all the negative areas generated by points in quadrants 2 and 4. And so then it will be a line again, and it will be a very strong negative covariance, sample covariance resulting from these data points. Yeah. And what happens when you have points that are like more or less all over the place because they are Gaussian noise, right? Engineers would like to say they are white noise. They are randomly generated. They are really spreading all over. No point is really making other points outlying. No point is really the dominant sort of center of the data cloud. So what can we say? Well, in this case, very likely your covariance sample as calculated based on this formula will end up being a number that is, of course, most likely positive or negative, but very close to zero. When it's very close to zero, then we have a cutoff and say that we cannot conclude anything. All right. So that will be an observation where we say this is covariance sample greater than zero, less than zero, close to zero, right? Close to or equal to. It won't for data that is measured from natural measurements, like stock market, height and weight, and all these things. You probably will never see covariance being exactly zero. So that's just a theoretical, um, sort of theoretical ideal or theoretical definition where covariance is exactly zero. But if it's close enough to zero, we can already conclude that there is no perceivable line. And just to complete the picture, because I keep emphasizing sample, more because we do draw um, measurements from real life, and most of the measurements that we draw from real life, they are a sample of a much bigger population. But then to complete our theoretical understanding, there is a population version, and I'm not going to put in pop here because we will just reserve the lack of suffix as a convention for referring to the population covariance. And the way we define population covariance, very simple. One out of, or basically the average of all the data points. All right. And because then we will need the population mean. Yeah. So that will be the population mean of X times yi, each data point's y value, minus the population mean of y. That's all. So essentially, it is the perfect average of all the areas generated by the difference from the x value of the data point from the mean of x, the population mean of x. You just change this to mu x, and the y value, the difference of the y value from the population mean of y. Change this to mu y. That would do. So it's just a matter of getting the symbols and the technicalities right. But the essential idea concept doesn't change. It's still based on averaging out the area. So in short, covariance is like a descriptive that is calculated based on averaging the areas induced by each of the data point in two-dimensional space because we're having two measurements, right? And essentially that's that. And if covariance can be positive, that means having an average positive area, average negative area, average area that is equal to zero or very close to zero, right? So that is the summary. And this summary has the meaning that if it's very large number, positive number, then it is aligned with positive gradient. If it is a very large negative number, then it is aligned with negative gradient, sort of tilted the other way. And if it's close to zero, then it is we are of the conclusion that there is no line perceivable. Now, imagine you build a robot that is capable of calculating this very quickly, and we can do that nowadays. It will be able to tell in real time as it looks around, it kind of pans its camera around and look at things and say, I see a line. Oh, that is not a line. That is exactly how we can make this robot really intelligent just by calculating covariance. So the power really lies in defining covariance and understanding it this way. All right. So I hope you see the motivation here. And once you can see the motivation, the formulas are like, of course, they have to be done this way, right? Okay. So I will just I'll leave you with that first, and then we move on to subsequent slides.